Hello, this is Daniel Fritz Mathematics coming to you, and tonight we're going to be talking about the concavity of a function. So with the concavity of a function, we want to let the function f be differentiable on an interval AB. Then, number one, f is concave upward on AB, on the interval AB that is. If f prime of x, or f prime, is increasing on the interval AB. When we talk about f prime, we're talking about the first derivative of that function. Number two, f is concave downward on the interval AB if f prime, which is a derivative of the function, the first derivative, is decreasing on AB. So, decreasing on the interval AB, as we look down here, we see some pictures basically of f being concave upward on the interval AB, and we also see f is concave downward on the interval AB right here, as you see. Feel free also to stop the video and repeat the video. Stop it, copy down notes, and take your time and try to understand what we're trying to explain here. So it's okay. So when we go to theorem 2, theorem 2 talks about if f double prime of x is greater than 0 for each value of x on the interval AB, then f is concave upward on AB. If f double prime of x, which is also the second derivative of the function, is less than 0 for each value of x in AB, on AB, then f is concave downward on the interval AB. Now, let's talk about determining the intervals of concavity of function f. So we want to determine the values of x for which f double prime is 0, or where f double prime is not defined, and identify the open interval determined by these numbers. And 2, determine the sign of f double prime in each interval found in step 1. And to do this, compute f double prime, that's the second derivative of c, where c, the critical point, or the the value, is any conveniently chosen test number in the interval. Now, if f double prime of c is greater than 0, it is concave upward on that interval. And if f double prime of c is less than 0, f is concave downward on that interval. Now, let's do a problem here. Okay? Let's determine where the function of f of x equal to x to the third minus 3x minus 24x plus 32 is concave what? Upward, and where it is concave what? Downward. So solution. We want to write the function over again, and here we want to take the first derivative. And when we take the first derivative, we come up with 3x squared minus 6x minus what? 24. Then we take the second derivative again. Second derivative, and we come up with here 6x minus 6. Now, after we take the second derivative, we will then set f double prime of x equal to 0. So we'll take 6x minus 6 and set it equal to 0, and also factor, right? Or, solve for x by factoring the function here, the second derivative, and also now calculating its critical points at that point. So with 6x minus 6 is equal to 0, of course we factor out the 6, the GCF, and then we come up with 6, right, parentheses, x minus 1 is equal to 6. Equal to 6, no, not equal to 6, but equal to, sorry about that, 0. There we go. We're going to correct that. We correct that mistake. So here we have Well, 6, okay, we set 6 equal to 0. You know that's not defined at that point. So here we say x minus 1 is equal to 0. And then we solve for x by taking positive 1 to both sides. And we end up with x is equal to 1. So now basically we can conclude, since x is equal to 1, we can conclude that f is concave what? Downward on the interval from what? On negative infinity to 1, and concave upward on the interval on 1 to positive infinity. And as you see this is only a sketch of the graph though. And we sketch the graph here. Here's basically when we're getting ready to get into an inflection point. So we won't get into inflection points in the next video. So right here is where from negative infinity to 1 is where it's concave what? It's concave downward. And then of course from this point on here, it's going to be from 1 to positive infinity is concave upward. So this concludes the video on concavity. Feel free, like I said, to go back and rewind. You can pause the video and also collect and also copy notes appropriately. And stay tuned for our next video.